Hi everyone. In this lecture, I'll continue with a discussion on channel models. In the last lecture, we analyzed mostly what we call as the line of sight communication in free space. But in a wireless communication system, in a practical system, you'll have what we call multipath propagation. So now we'll first analyze the fundamental mechanisms by which the propagation occurs and then try to do a mathematical analysis for the channel model. So eventually the goal is to predict what is the power level that your base station or your cellular station receives from the base station. So that's our goal eventually. Okay. And if you recall, I discussed in the last lecture, there are two big mechanisms. One is called the large scale effects and the other one is called small scale effects. So first, what we are going to discuss right now in this lecture is what we call the large scale effects. So which is your cell phone, the model that we are going to develop in this lecture will be applicable if your cell phone moves for much longer distances, several wavelengths away. It's like tens of wavelengths away. Okay. If the cell phone is going to move for short, very short, a few wavelengths, then this large signal model's power, whatever power we predict, is not going to change much. Okay. So then in reality, the cell phone, the power received by the cell phone will change significantly even if it moves by few wavelengths, 1 or 2 wavelengths or few wavelengths. And that we will be capturing it in the next lecture, which is in the small scale effects. Okay. But the fundamental mechanism of wave propagation is same, whether it's small scale effects or large scale effects. The fundamental mechanisms of wave propagation is same. So there are electromagnetic light is electromagnetic waves can be seen as light. So like light, they will undergo reflection, diffraction and scattering. So shown here is an example of reflection. So where you have the base mobile station here and a base station here. So there is a direct line of sight path from the base station to the mobile phone. But there is also a reflected path. So reflection happens when the surface is really smooth. You have a very smooth surface and an incident wave, a plane wave is incident. You can treat them like straight lines. Okay. For light can be treated like that. If the incident wave is a plane wave and the surface is really smooth, then you can treat them like it can be treated as a rectilinear. There is the theory of rectilinear propagation of light. You can treat it like analyze it using very simple the theory of rectilinear propagation of light. Okay. So here if you see, I've shown here two paths. Reflection can happen anywhere. It can, for example, let's say we had an obstacle here, a wave can hit this in some angle and it can reach here. Okay. Reflection again has to obey the Snell's law and all that, so you have to keep that in mind. Again, that's not important for us now. The main thing is to understand what are the mechanisms by which the signal can reach. So here if you see, multiple paths of the signal reaches the cell phone. And as we discussed, when multiple paths reach the cellular phone, you are going to have constructive and destructive interference. So in that case, what is the change that we'll have to include to the path loss models? So that's what we'll be analyzing now. The second phenomenon is what we call diffraction. So diffraction happens when there is sharp edges. So when a wave, for example, hits this region, from Huygens principle, it will generate secondary waves which will be propagating in this direction. So again, this can be explained. I probably have a GIF for this. Yeah. So here, if you see, this is more like a 180-degree radiating antenna, radiating source. It's radiating at this edge. When the signal comes here at this edge, there is a secondary wavefront which is developing, and we can see that. Okay, it's traveling in this direction. Okay, we are getting power even in this direction. The red one, if you follow the red curve, okay, that's showing the power in this direction as well. So this is how, for example, even though there is no direct line of sight path between so sometimes what happens is, even if we don't have a direct line of sight path, if you see here, there is no direct line of sight path from the base station to your mobile station. But still, because of diffraction, let's say there is a very tall building and it's obstructing it. The tall building, it can undergo diffraction and your signal can reach here. Okay, or the building can partly absorb the signal and then it can literally go through the building and come also. But this will be normally very weak. Through diffraction the signal can reach. Again, that power level will also be very weak. It's a secondary wavefront, so the most of the power will be going in the main direction. Okay, part of it will be diffracted. And this diffraction can be explained only using wave theory of light. Okay, because light is a wave, I mean a wave theory of electromagnetic waves, it's a wave, so it will undergo diffraction. So that's what is, I probably have another GIF to show as well. So here if you see in this waveform shown here, you can actually see there is a secondary wave generating here. So there is a sharp edge here. So from that you can see there is a secondary wave propagating in this direction, of course, albeit of course of a much lower intensity, but you can see that. Okay, a plane wave is incident on this sharp edge here. So suddenly we have secondary wave fronts traveling in this direction. So this is what we refer to as diffraction. Now diffraction is also another mechanism. Now all these mechanisms are going to give us multiple paths at the receiving antenna. The third mechanism is called what we call scattering. Scattering happens, so this is an incident plane wave when there is irregularities on the surface. So it can happen externally. Let's say you're walking and talking on, let's say the building surface may not be even, it may not be perfectly smooth. Okay, in that case it might undergo scattering. Now what is uneven, what is not smooth is when the irregularities on the surface of your where it is getting scattered should be comparable to wavelength of the light incident wave. Then you will actually see the effect of scattering. So you will actually see the effect of scattering, the light getting incident, but they are all traveling in different directions. Okay, so the paths that these signals take to reach the mobile phone will also vary because of this scattering. The same signal scatters into multiple paths and reaches. Now I'll analyze what happens. I'll just give an expression, not even analyze what happens when you just have two paths. So then you can see what is the effect of this multipath for the large scale effects. So let's say we take a very simple problem. Previously the path loss model, free space path loss model, lambda by 4 pi r square into pt gt gr. So this result was valid divided by L, where L is accounting for other losses. L is greater than 1, okay, or equal to 1. Now this is a model which was valid for a line of sight communication. But when you have two paths, like this, again the derivation is given in your textbook. You don't need to know that. You need to know the final result, which is an interesting result to interpret. If you know the height of the transmitting antenna and the height of the receiving antenna, where HT and HR are height of the transmitting and receiving antennas, and GT and GR as the gain of the transmitting and receiving antennas, then again in the far field region, where far field here refers to root of HT HR, okay, then the received power is going to go down as 1 by r power 4. Okay, so from r square, if you just have two paths, the received power actually goes down as 1 by r power 4. So it decays down much more. Okay, so that's the problem when you have multiple paths. Multiple paths usually means your path loss will be much worse. So here for just a two-ray model, where you have one direct line of sight path and one reflected path, your signal power is going to reduce at the rate of r power 4. So if I increase my distance from, let's say, 1 meter to 10 meters, then my power will be reduced by 40 dB per decade. Okay, that's a 1 decade change in the distance. You will have, so 10 log of r power 4, when you compare to 1 to 10, you will get 40 dB. So it's going to power is going to roll off at the slope of minus 40 dB per decade. So all I'm trying to show in this model is that with multipath you can have much worse roll-offs of power. Your power will change much more rapidly than what it was for a line of sight communication. So now, of course, when you have just two paths, the analysis becomes much more complicated. When you have multiple paths, the analysis becomes even more complicated. So then how do we actually derive general expressions for path loss? Because you are going to have many such paths. What I have taken is one example. So in that case, what we do is, I have already discussed this in the previous lecture. So we will start with the expression for your path loss in dBm. So this is the received power. I already discussed that. Instead of using the direct expression for the path loss models, we will now assume that the received power is inversely proportional to r power n, okay, where n is what we call as path loss exponent. So if you know the received power at a distance r0, which is in the far field region, okay, then you can compute the received power at any distance using this equation. So P or of r at a distance r is simply given by, if you know the received power at r naught, it's going to be r naught by r the whole power n. Okay, this result makes intuitive sense because at r equal to r naught, this power will be equal to this power. That's the power at the distance r naught. At any distance after that, it's going to roll off as 1 by r power n. So this is satisfying this equation. Okay, so after r naught, once you for r greater than r naught, this expression is valid. For r greater than r naught is a constant. So the power is going to just, the only dependence is p of r naught is also a constant. So this result, this expression p of r is simply proportional to 1 by r power n. So if I take logarithm on both the sides, so what I'm going to do is that p r of r divided by 1 milliwatt equals p r of r naught divided by 1 milliwatt into r naught by r the whole power n. So I'll take 10 log on both the sides. So this will become in dBm and this will become in dBm. Okay, this will be in dBm and you will get 10n log to base 10 of r naught by r. Also, we can just rewrite this expression a little bit, or I can simply say, if you want to find, this is again, you can also express your result in terms of path loss, where I'm going to define a term called PL of R is what we call as path loss. Okay, so the path loss is simply going to be the, actually this expression is nothing but path loss at a distance r naught here. So this, I think I should be a little bit clear about specifying it. The path loss at a distance r naught, PL, is what we call path loss at a distance r naught, is simply given by Pt, the transmit power, divided by Pr at r naught, and then you take 10 log of this. So path loss is a dimensionless quantity. Okay, so that will have units of dB. So it should be clear here. Whenever you are measuring power, I'll normally measure power with respect to 1 milliwatt. So I have to mention dBm. So I have to tell that, okay, look, this is measured with respect to 1 milliwatt. But here it's a path loss is purely a ratio of 2 powers. So I don't need to tell what is the reference I'm measuring with. I mean, there is no need as well. So you can directly, path loss will have units of dB. So this term, let's say Pt equals, or Pr of R equals Pt into some constant divided by r power n. So then this whole term I can call Pt is the transmit power. This whole term I can call it as path loss at a distance r, PL of r, in a linear scale. This is in a linear scale. In a logarithmic scale, it will be proportional to, path loss will be proportional to here. So now here this term, okay, I think there is a minus here because path loss is a positive number. Okay, it's a positive number. I mean, it's going to be a, so here I have subtracted. If you see here, Pr of r, so let me say Pr of r on a linear scale is going to be Pt into PL. PL of r is the path loss at a distance r. So if I divide by 1 milliwatt and take 10 log on both the sides, I'll get this expression. Okay, Pr of r in dBm will be the transmit power in dBm minus the path loss in dB. So I think I gave a question like this in midsum, wherein I gave the path loss directly. You just had to subtract it from the transmit power. Okay, so the path loss, now you have to now find, okay, you have expressed your result in terms of path loss, but what is the expression for path loss itself? So if you know path loss at a distance r naught, so if you see, path loss will now increase as you move, right? Because if your power is reducing, means path loss is increasing. Okay, so I think I just made let me correct this again. I'm sorry. Pr of r is actually Pt by PL of r. I'm sorry. So PL is greater than 1. So PL is greater than 1 on a linear scale. Okay, so path loss, we are saying it's a loss, so it's greater than 1 on a linear scale. On logarithmic scale, it's greater than 0 dB. Okay, it's Pt by r, so that's why you get the minus here. Okay, so now the next goal is, how do you find path loss? The same way we will define the definition for a path loss at a distance r. If you know the path loss at a distance r naught, if you know the path loss at a distance r naught, it's going to increase, your path loss is going to increase with distance. So it's going to be 10 log of r by r naught. So I made a small mistake here. So this is either minus of 10 log of r naught by r, or plus it should be r by r naught. So it should increase, because your path loss should increase as you increase your r. So if you know the path loss at a distance r naught, so this is, I'm plotting path loss as a function of r. At a distance r naught, if you know your path loss, then you can find it at any distance provided you know the path loss exponent, okay, from this equation. That's what is given here. Okay, so let me just write that equation alone here. So path loss of r in decibel will be equal to path loss of, if you know the path loss at a distance r naught, plus 10n log to the base 10 of r by r naught. So that's the only difference. There's a small mistake here. Okay, or if I just want to retain this entire expression as it is, if you want to use it, then make this as minus. Okay. Okay, so now often we said that the path loss, actually, how do we find that? If you want to know the path loss, once you measure it at a certain distance, it's going to vary. I mean, you also need to know the value of n, the path loss exponent. So how do we find that? I've already very briefly discussed in one of the previous lectures. So the standard procedure is, if you know if this is your distance where you're radiating, for an isotropic radiator, what you'll do is you will find the path loss at different distances, okay, or you can directly find the received power at different distances and then plot them on a received power versus distance graph and find the best straight line equation which fits this. So here you should understand the received power is in log dBm. This is in dBm, distance is also in dB. So this is 10 log of r, 10 log of r, okay, r by some reference distance r naught. So in that case, you just have to fit a straight line equation, so such that you just minimize the mean error. When I said MMSE sense, minimize the mean squared error. Okay, so you find this straight line equation, find the distance between these 2 points on the straight line to this, and ensure that the error is minimized. Okay, in a minimum mean squared error sense. So then that straight line, using that, you know the path loss exponent from that graph. So that path loss exponent is what we'll be using for estimating the received power. Okay, so finally, I'll just briefly touch upon this model. So we just discussed now that we discussed how to characterize the losses in a wireless channel. Okay, so when you have more than one path, we are going to have destructive interference, and the received power is going to be falling at a rate greater than r square. And we said we'll say that is n, and n is the path loss exponent. But now you should understand, an engineer, a communication engineer, cannot use the same model everywhere. I mean, he cannot use the same model everywhere, because the path loss models will depend on the location where you take your measurements. Some location may not have many buildings, so you might actually have good line of sight path itself. Some locations may have a lot of trees in between. That can also give rise to a significant loss in the received power. Okay, so in that case, it's purely location dependent. Again, when something becomes very specific, when you want to characterize something, when you want to develop a model and you need to know a lot of information, then the best way is to be always resort to statistical models. Okay, instead of saying that, okay, what is it, instead of finding path loss model for every terrain and every forest or different regions, we'll say, okay, let's go for a statistical model, and from the statistical model we'll try to give you what is the probability that you will receive a certain received power. Okay, the moment we go for a statistical model, you can't exactly tell me my received power at r, you cannot exactly define it. You can only say, okay, you will receive this power with a certain probability. Okay, so now what we can say is, this is the expression. If I want to find, if I know the path loss at a distance r, then if I know a path loss at a distance r naught, then all I need to do is that I just need to find so again here there is a plus here, I think. Okay, I'll just clarify this. This is plus, obviously, because path loss is an increasing number here. We are subtracting path loss from this expression here. so it has to decrease. So that's why there is a plus here. Okay, so I'll update this in the slides when before I post it in the Google Classrooms. Okay, the Google Classroom page, I'll just update it before that. Now the receive power here what I've shown here is the path loss model. The path loss at a distance r. So if you recall, the path loss on a logarithmic scale will look like this. Okay, instead of here, this is a deterministic model, which means at a distance r0 I know the path loss, and at any distance I can exactly tell you what the path loss is if you know it here. But instead of saying that, I'm going to add a variable x in decibels. Okay, the unit of this x is in decibels. Okay, this variable is going to have a mean of 0 dB and a variance of sigma in decibels. This will also be in decibels, and this will be a Gaussian random variable in decibels. So that's a distribution is what we call log normal distribution. I'll talk about log normal in a moment, but I just want to introduce that such a distribution is what we call as a log normal distribution. Okay, so instead at this point, at every point, okay, the received power or the path loss, you can plot anything. You can either plot the received power as a function of distance. So for every distance, the received power as a function of r, you are going to have a Gaussian distribution around a nominal value. P r of r, I'll call it bar, that is the average value or the mean value you will receive, but you will have some kind of a spread around it. So that's what statistics is all about. It tells you, it doesn't give you the exact value, but rather with a certain probability, what is the probability with which it will be greater than that or less than that. So now we will spend some time understanding how the model is done or how the model is actually developed for this. So again, there is a plus here. So the path loss models is going to be this way. Okay, so now you should understand this x here in decibels will go from minus infinity to plus infinity. Okay, so it will go from minus infinity to plus infinity. That should make sense, because if you recall, your path loss, your actually the received power of r at a distance is simply given by transmit power divided by the path loss at a distance r. If you see your path loss, it can be, since it's a statistical number, okay, around the mean it can have huge variations. Okay, see here, let me just come on the linear scale. I'll talk about the linear scale. Ideally, let's say there was no losses at all. There were no losses at all. Then ideally the value of path loss at a distance r is going to be just 1. There is no losses. But typically the value of path loss is going to be greater than 1. Path loss can be greater than 1. Or path loss can be less than 1. If path loss is less than 1, then we say that in fact we are saying, okay, there is in fact some gain from, maybe you're having some constructive interference and you're getting some gain out of it. Okay, because if your path loss is less than 1, your receive power can be greater than the transmit power. That may not happen. Okay, but with some constant, probably we can define some constant. Conventionally, to a conventional system, your signal, your power can be higher. When I'm comparing it with some nominal lossless system, maybe I can get some higher power. So it's a statistical model, so you will have some conditions like that, but those conditions will have very, very low probabilities. So your path loss model, all I'm saying is that in a linear model, it's a positive number. Path loss is always a positive number. It can go from 0 to infinity. If path loss is 0, then the receive power is infinity, because it means there is huge gain, but that's never a probabilistic event. That's highly improbable. Similarly, if path loss is infinity, which means you're going to lose so much of power that the receive power will be 0. Again, that's a improbable condition. Okay. So on a dB scale, I told you 1 is the nominal case, which means there is no loss at all. If path loss is 1, PR equal to PT, there is no loss at all. And from 0 to 1, if your path loss is between 0 to 1, it means that your receive power is higher, you're getting good gain. The path loss is between 1 to infinity, which is normally the case, okay, then you're actually losing out a lot of power. So this makes sense. 1 should be like your center, 0 should be one end, and infinity should be other end. Now if you just take log of that variable, log of this variable, then you will convert 0 to minus infinity, 1 to 0, and plus infinity to plus infinity. So that's called log normal distribution. I'll probably discuss it in a more deeper sense. Now if you look at this path loss model, this is the expression for path loss here. I have written this is plus here, okay. So path loss should increase. So in the path loss model, there are two unknown variables. See, PL of R0 is something you are going to measure it. You are going to measure the power at a distance R0 or path loss at a distance R0. Okay, if you measure the power, you can calculate the path loss. So let's say if you measure the received power at a distance R0 and then you divide it by PT, you are going to get the path loss at a distance R0. Okay, so this is a linear scale and you take 10 log of that, you get path loss in decibels at a distance R0. Once you know that, then all you need to know is the path loss exponent n and the variance of this random variable x in dB. If you know these two, then you have all the statistical models available to you. You have completely characterized the channel. So you can say what is the probability that I am going to receive a certain received power, or my received power is going to be greater than a certain number. Okay, so that's about the statistical modeling of the path loss. So this I'll just talk briefly about log normal distribution. So in a log normal distribution, it's nothing but x is a variable which is going from 0 to infinity, and when you take ln of x, this y will be a Gaussian random variable. Okay, logarithm of some variable which goes from 0, I told you why it goes from 0 to infinity. Your path loss is a positive number, okay, because you're just going to take the ratio of your transmit power divided by the receive power at any distance r. Okay, so obviously it's a ratio of two powers, it's always positive. Okay, so path loss is always positive, so it will go from 0 to infinity, and when you take ln of that, it's going to go from minus infinity to plus infinity. So this distribution is what we call log normal distribution, okay, where y happens to be a normal distribution, meaning it has a mean 0 mean will be 0 decibels, okay, which means path loss equal to 1 is like the mean, okay, is or some fixed path loss. It can be some nominal path loss. I said 1 here, but it can be some nominal path loss, 1 or 0 dB, okay. And so for example, what I'm saying, what do I mean by that is, I can divide x by some PL nominal path loss, and then take log of this, okay, log to base e. Then also in that case, the mean is going to be PL of norm. I mean, mean is going to be 0 dB, but there the 0 dB, we are comparing it with some nominal path loss. Okay, so now the mean for this is going to be x equal to 1 or y equal to 0 dB. Okay, so this is what I meant. I said x equal to 1 for this variable here, or it can be x equal to PL of some nominal value. Mean can be even there. I can shift it to that point. Some path loss, some nominal path loss value. Okay, so now then once we know that y is a Gaussian random variable, now y will be a Gaussian random variable with a mean of 0 decibels and variance of sigma. Now if I tell you what is the probability that the received power, okay, received power is greater than a certain gamma here. So now see this, once you know the path loss and everything, you can then model what is your received power, right? Once you know the path loss model, so then I can say received power will look something like this. So this is P r of r at a distance r. I'll call hat as the average value. So that's what I'm going to call it as mean at r. And what is the probability it is greater than gamma? That's what we are more interested in finding. It should be greater than some threshold, so that that threshold should be more than your cellular phone sensitivity. That's what we are interested in finding out. So first I'll just start with a very simple Gaussian random variable problem. Let's assume we have a Gaussian random variable with probability 0 mean and a variance say sigma, a 0 mean and a variance sigma. Then if I ask you to find what is the probability that this random variable y is going to be greater than beta, where beta is of course greater than 0, okay, or gamma here, I'm sorry, this is gamma. So y is greater than gamma is given by q of gamma by sigma. So if you recall what is q function, I think I have definition of q here. Anyways, I'll just write the definition of q. Yeah, the definition of q function. So this is nothing but I've shown the log normal distribution here. See, you should treat it as a Gaussian distribution with zero mean and a variance. The only difference is the variables along the x-axis will be in dB units. That's the only difference. Okay, and it can be your received power. We'll come to that little later. Okay, but right now I'm just talking about a log normal distribution. The axis here is going to be in, this is y, it will be in decibels. Now the probability here is nothing but you are supposed to find what is the probability P of y is greater than gamma. And we should know that for a normal distribution is nothing but a Gaussian distribution with zero mean and variance 1. If you take the variance as 1, then it's called normal distribution. And the q of x is defined for a normal distribution as probability of x, or let me call this as y greater than x. That's how we defined it for a normal distribution. Okay, so this nothing but is equal to q of x. So q of x, if you see the definition of q of x, goes as 1 by root of 2 pi sigma square integral x to infinity e power minus x square by 2 sigma square dx. Now if I have, this is x square by 2 square, x square by 2, there is no sigma there, sigma is 1, so it will be simply 2 pi sigma. So if this result, if I want to convert it to a Gaussian random variable in terms of a finite sigma, then all I need to do, this gamma is actually for a Gaussian random variable with a variance sigma. So you just have to make some substitution called some t equals x by sigma, and you will actually get this result as this result. If let's say I define q of gamma for a zero mean random variable with a finite gamma, then it's going to be finite variance. Then this limits will actually go from gamma by sigma to infinity. Okay, dx by sigma, you will get this result and you will get this expression. So I have already derived this in the previous lectures. I'm not going to go there. I probably didn't give a better explanation here, but I've already done this, so I think you know this by now. So I'll leave it at here. So this expression should be pretty simple. So what is the probability that y is greater than gamma? So from this graph, the area under this graph should be equal to q of gamma by sigma. Okay, I have derived this result in the digital communication section initially. It's a very, very simple result. I think so you can try it yourself. So q of x is defined for a normal distribution with unit variance and zero mean. So q of x is given by x to infinity e power minus x square by 2 into dx. Now what we are asking you to find here is, this is a Gaussian random variable with a finite sigma. We are asking you to find root of 2 pi sigma square integral gamma to infinity e power minus x square by 2 sigma square dx. So this is what this integral is. Okay, so all you need to do is make a substitution, x by sigma equal to t. Okay, then you will get an expression like this. You will actually get this here. I'm writing it here. You will simply get 1 by root of 2 pi integral gamma by sigma to infinity e power minus t square by 2 dt. So this is nothing but q of gamma by sigma. So that's what I meant. Okay. Now what if this distribution has a finite mean mu? In that case, how does this expression change? How does this expression for this area change? Okay, so you should understand this distance was, what matters to us is this distance. Okay, this distance is what that matters. So from the mean, you have to compute it. So here the graph will simply be q of gamma minus mu by sigma. Okay, so there is, in fact, if let's say I give you this Gaussian random variable with a finite mean, then you'll have to evaluate this integral, 1 by root of 2 pi sigma square integral gamma to infinity e power minus of x minus mu the whole square by 2 sigma square dx. So this is the value of this integral shown in this blue here. Okay, so this integral, you have to make a substitution x minus mu by sigma equals t. Then the limit here, this limit, this integral will become something like this, 1 by root of 2 pi, because dx will become dx by sigma will become equal to dt. So dx here is sigma, if you take it out you will get replace it as dt. So then you will get integral gamma minus mu by sigma to infinity e power minus t square by 2 dt. So again this is nothing but q of gamma minus mu by sigma. Okay, and similarly gamma can be even less than mu. So this will be helpful in finding what is the probability that your signal power is lower than the mean by a certain value. Then you will have a call will get blocked. Gamma can be even less than mu. In that case the only change here will be simply q of mu minus gamma by sigma. It's the same thing. This distance is what that matters. So you should keep this in mind. Okay, so just to quickly reiterate properties of q function. So if let's say for a Gaussian distribution with zero mean, if you are asked to find a distance here from the mean, you are away by say a value of x in this direction, and again you move x in this direction. So I will call it minus x here, this will be plus x in this direction. Then this area will be exactly equal to this area. This is called the tail probability. Okay, and that for a Gaussian variable, and that will be same. So that's why I have written this here. So mu minus sigma will be positive divided by mu minus gamma will be positive divided by sigma. Okay, again this is a typo here. I'll correct all these typos when I upload the slides. So this is y greater than gamma. Okay, again this is y less than gamma. So that's why we are trying to compute this probability. Now using this result, in the next lecture I'll make another video to tell you how to calculate. We will go a little bit more deeper about the power received by a cellular phone and what is the area of coverage. Eventually we have to come to that result. Right. So now so far in this lecture, to summarize what we have discussed so far is that we have come up toward the end of this lecture. We said in a wireless communication you will have multiple paths. You will actually have multiple paths. Because of this multiple paths, your path loss is going to be much worse. And because of that we said we have to find a path loss exponent called n. And we first started with saying that, look, if I know a received power at a distance r0, which is in the far field region, and I know the path loss exponent n, and this we find using that direct on the field measurements and from an extrapolation or from the curve fitting graph, a straight line curve fitting graph. Okay, once I know that, then I can use this to estimate the received power at any distance. But then we said this n keeps changing from place to place, and the measurements, the measurements also have to be taken at many locations. So we cannot have a deterministic model. Instead we should go for a statistical model. So when we go for a statistical model, that's when we introduced what we call as a log normal distribution. A log normal distribution is, once you take logarithm of the variable, that will be a Gaussian distribution. The logarithm of some variable will behave like a Gaussian distribution. And we just quickly studied what is log normal distribution, and here if you see, this result is important here. Okay, I'll clarify about the plus minus signs, because your textbook might be using a different sign. I'll just clarify this. But path loss should be positive, so because you are subtracting path loss from this, so I'll clarify that a little later. Okay, and your received power, when you're writing it in here, this path loss exponent here has a random variable, so it's going to be a random variable. So the received power can actually be plotted. If I ask you to tell me what is the received power, you can't tell me the exact value, but you will give me the probability distribution. So P R of R, it's going to be something like this. So this will be P R of R in dBm. So this is in distance, can also be measured as a ratio of the distances, or you can mention even as a Gaussian distribution. The received power can be mentioned as a Gaussian distribution. Okay, so there will be average power, received power in dB or dBm. Okay, So we'll call it P R of R hat, an overline on top of it in dBm, and it will be having some variation around it. And those variations can be captured using a statistical model. So all you need to know for this model is if you know the receive power at a certain distance or not, and path loss exponent. Previously we said these two were sufficient for a deterministic model. But now you should also know the statistics of the log normal distribution X, whose mean is anyway 0, but variance sigma in decibels. You should have a knowledge of sigma as well. So you need to know sigma, you need to know n and the receive power measurement result. Then you can have a statistical model characterizing your path loss. So this more or less summarizes everything you need to know about the large scale effects. So for a distance r, you know what is your receive power. In the next lecture, we will try to come up with some practical numbers and see what is the area of coverage. If you give a tower and then say the distance, what is the probability with which you are going to cover a certain distance. Okay, those are all important parameters for cellular operators. Okay, so yeah, I'll upload that in the next lecture.